Nearly 14 billion years back, an event defied all logic. Our cosmos burst from a point tinier than a proton, birthing time, space, and existence as we know it. Yet here's the revelation that changes everything. Modern researchers have proven the Big Bang wasn't our true origin story. Something far more bizarre existed beforehand. Not empty void, but a quantum realm alive with hidden forces, a domain where physical laws themselves took shape. We're embarking on a journey through collapsing realities, infinite rebirth cycles, and a discovery that emptiness may hold the greatest power imaginable, ready to witness how existence pulled itself up by its own bootstraps from sheer impossibility? Tap that like button and join the unfolded late science community. Here we go. Envision the blackest region of the cosmos your mind can conjure. 0 stars, 0 worlds, 0 illumination, pure void extending without limit. Now brace yourself for what researchers uncovered. That void is actually a fiction. When quantum physicists scrutinized the vacuum using their most advanced frameworks, they stumbled upon something extraordinary. So-called empty space teems with invisible power. Consider the sea on a windless afternoon. From a distance it appears glassy and motionless. Draw near and you'll notice microscopic waves, fleeting disturbances emerging then disappearing. The quantum vacuum operates identically, except these ripples are unseen energy fields pervading all locations perpetually. This finding represents verified science, replicated in research facilities worldwide. The vacuum harbours what scientists term zero-point energy, the minimum possible energy level that still contains detectable force. You cannot extract it, you cannot disable it, it's interwoven into reality's foundation. Here's where things turn peculiar. This power doesn't merely exist passively, it moulds our universe. When physicists position two metallic surfaces incredibly near each other within a vacuum, they experience a push toward one another from this unseen influence. Researchers label this the Casimir effect, measured with exactitude. The vacuum separating the surfaces holds less power than the vacuum surrounding them, generating an asymmetry that produces genuine physical force. This discovery means what we label as nothingness possesses architecture. It carries attributes. It submits to measurement, manipulation, and investigation. Ancient thinkers from Greece believed removing all substance from a region would yield absolute nothingness. They erred. Contemporary physics outlaws it. The consequences destabilize our comprehension of being. If the vacuum carries power, then nowhere across the cosmos remains genuinely vacant. Every cubic measure of space holds this baseline hum of quantum motion. When you gesture through atmosphere, you traverse an ocean of invisible energy that preceded the earlier star's ignition and will outlast the final one's extinction. Yet quantifying this energy spawned a dilemma haunting physicists today. Reality hides secrets where nothing meets everything. When they computed how much energy the vacuum ought to possess based on quantum principles, the figures skyrocketed. The forecast value emerged 120 orders of magnitude vaster than observation reveals. Picture predicting someone's mass at 10 pounds, then learning they actually weigh less than one atom. The discrepancy stretches that monumentally. This crisis reveals something profound. Our grasp of what nothingness truly represents remains incomplete. The vacuum conceals mysteries potentially explaining the genesis of all things. Scientists confirmed empty space bears energy, but the enigma of why it bears precisely the quantity it does stays unsolved. What unfolds when this quantum foam experiences disruption? The quantum vacuum doesn't just store energy, it generates substance. At this very instant, in the gap between your vision and this display, particles materialize from nowhere. They persist for a fractional heartbeat, then dissolve back into the void. Scientists name them virtual particles, and their presence has been validated through experiments measuring their influence with breathtaking precision. Here's their mechanism. Power and substance interchange, as Einstein demonstrated. The vacuum possesses energy, and that energy perpetually fluctuates. For the most fleeting instant, a fluctuation grows massive enough to divide into a particle and its antimatter counterpart, an electron and positron, for instance. These pairs erupt into being, survive for a duration shorter than comprehension allows, then collide and eradicate one another. The energy reverts to the vacuum. The cycle repeats ceaselessly. This occurs trillions upon trillions of times each second in every cubic measure of space. The vacuum isn't serene. It's a violent tempest of genesis and obliteration happening at scales far beneath anything we perceive directly. Yet we recognize these virtual particles as genuine because they leave traces. During the 1940s, physicists detected something peculiar about hydrogen atoms. The energy configurations of electrons circling the nucleus didn't perfectly align with forecasts. The variance was minuscule, yet present. After rigorous inquiry, they realized virtual particles bore responsibility. These phantom particles momentarily interact with the electron, adjusting its energy by a quantifiable amount. Scientists call this the Lamb shift, proving the vacuum isn't dormant. It's animated with quantum activity. The proof becomes even more persuasive. Virtual photons, light particles blinking in and out of being, generate a phenomenon termed vacuum polarization. They temporarily shield the electric charge of particles, influencing how forces operate at quantum dimensions. Without virtual particles, quantum physics mathematics would crumble. They're not supplementary, they're foundational. Contemplate what this implies for the question of nothingness. If the vacuum spontaneously generates matter even for microseconds, then complete nothingness becomes forbidden. Nature refuses it. The universe possesses a baseline chaos level embedded in its foundation. But here's the disquieting aspect. If virtual particles can manifest from the vacuum for tiny time fractions, what prevents a larger fluctuation from occurring? What blocks the vacuum from generating something permanent? Something that doesn't vanish? The solution involves a principle making nothingness even stranger than imagination allows. During 1927, a German physicist named Werner Heisenberg uncovered a rule shattering our common-sense grasp of reality. It declares you cannot simultaneously know both the precise location and exact velocity of a particle. The more accurately you gauge one, the less you comprehend about the other. This isn't an equipment limitation. It's a fundamental trait of nature. The universe itself prohibits certain information from coexisting. Now apply this to power and duration. The uncertainty principle also declares that energy can oscillate wildly, provided it happens rapidly enough. The briefer the time span, the larger the energy oscillation nature permits. This explains virtual particles' existence. The vacuum borrows energy to manifest them, then repays it so swiftly that the universe's ledgers balance. Here's the vital insight validated by decades of experimentation. The uncertainty principle ensures the vacuum can never achieve complete stillness. Fluctuations will perpetually occur, always. Quantum uncertainty makes perfect silence impossible forever. You cannot possess a condition of perfect nothingness, because that would demand knowing the exact energy at an exact moment, which nature forbids. Imagine photographing a hummingbird's wings during flight. Your lens captures blur because the wings shift too quickly. The quantum vacuum behaves similarly, except rather than motion blur, you obtain energy blur. The vacuum fizzes with possibilities never quite settling into calm. This carries staggering implications. Before the universe materialized, if ever a condition of genuine nothingness existed, the uncertainty principle would instantly annihilate it. Quantum fluctuations would surface, energy would spring forth, the void would destabilize. Scientists measure this instability in laboratories. When they chill systems down to temperatures approaching absolute zero, the coldest achievable temperature, quantum fluctuations become the sole motion remaining. Atoms still shiver, fields still oscillate. You can extract heat, extract particles, extract light, but you cannot extract the quantum uncertainty, keeping the vacuum restless. This isn't conjecture or philosophical speculation. Teams of physicists have detected these fluctuations directly by examining how light behaves in meticulously controlled experiments. They've quantified the vacuum's random electric fields affecting electrons. They've witnessed the spontaneous discharge of photons from atoms triggered by vacuum fluctuations. The evidence overwhelms. The uncertainty principle generates a paradox when we contemplate the origin of everything. If nothingness cannot exist because quantum statutes prevent it, then something has perpetually existed. Either the universe endures eternally or it sprang from a quantum condition that was never genuinely vacant. But there's a third option sounding like fiction yet might represent confirmed reality. Picture standing on frozen water. The ice appears solid, feels secure, but beneath the surface the water runs warmer than expected. The ice occupies an unstable configuration, awaiting the proper catalyst to collapse. This represents what physicists term a metastable condition, something appearing stable yet not truly at its minimum energy. The vacuum of space might resemble that frozen surface exactly. According to quantum field frameworks validated through particle accelerator data, the vacuum can occupy different energy conditions. There's a true vacuum, the absolute minimum energy achievable, and false vacuums perched at elevated energy tiers but remaining stable for extended durations. Our universe might presently occupy a false vacuum, and that terrifies certain physicists. Here's the reason. A false vacuum is metastable. It can abruptly decay into a true vacuum condition if the correct quantum fluctuation manifests. When that transpires, a bubble of true vacuum materializes and expands at light velocity, transforming space itself. Everything captured in the expanding bubble undergoes restructuring. Physical statutes change. Substance as we comprehend it ceases existing. Sounds apocalyptic, but reverse the viewpoint and you obtain something remarkable. What if the universe itself initiated as precisely this kind of occurrence? What if before our bang there existed a false vacuum that decayed into our reality? This framework has mathematical backing through something termed the Wheeler-DeWitt equation. It characterizes how quantum conditions evolve within the context of gravity and cosmology. Researchers in China released work during 2014 demonstrating that solutions to this equation allow a microscopic bubble of vacuum to materialize spontaneously from quantum fluctuations. Under particular circumstances, this bubble doesn't implode. Instead, it inflates, expands, and generates a universe. The false vacuum preceding our cosmos would have been unimaginably tiny, smaller than an atom, potentially as minuscule as the Planck length, which measures 10 to the negative 35 meters. At that dimension, space itself becomes granular, and quantum mechanics dominates everything. The conventional rules regarding cause and consequence disintegrate. Events can transpire without prior causes. Fluctuations can generate structure from randomness. This represents confirmed physics at quantum dimensions. We witness it in particle physics experiments constantly. Extrapolating it to the universe's genesis requires a leap, but it's a leap anchored in established science. The metastable false vacuum provides us a portrait of pre-bang reality. There existed no swirling vapor, no primordial substance, no time advancing forward. There existed only a quantum condition hovering in an unstable arrangement, anticipating the fluctuation that would spawn everything. How do we recognize this quantum energy accomplishes more than merely existing? Energy possesses mass. It warps spacetime, and the vacuum's energy presents no exception. Einstein's equations of general relativity inform us that both mass and energy generate gravity. A sphere of vapor generates a gravitational field. So does a light ray. So does the vacuum's energy. Despite being distributed across empty space, this forecast has been tested and validated in multiple fashions. The vacuum energy manifests as what Einstein termed the cosmological constant, a figure describing how much energy inhabits each cubic meter of empty space. For decades, scientists presumed this constant equaled zero. They were mistaken. During 1998, two astronomer teams made an observation shocking the physics establishment. They measured distant supernovae, exploding stars serving as cosmic distance beacons, and uncovered something impossible. The universe's expansion is accelerating. Galaxies flee apart faster presently than they did billions of years prior. Gravity ought to decelerate expansion. Matter attracts matter. The universe should be slowing, possibly even contracting. Yet the data displayed the reverse. Something was driving space apart. The sole explanation fitting the mathematics is vacuum energy. Empty space harbours a modest but non-zero quantity of energy density. And this energy possesses a peculiar trait. It generates repulsive gravity. Instead of drawing things together like ordinary matter, vacuum energy thrusts them apart. The more space expands, the more vacuum gets manufactured, which produces more repulsive force. It's a runaway mechanism. Scientists label this enigmatic component dark energy, and current measurements indicate it constitutes roughly 68% of total energy in the universe. Reflect on that. More than 2/3 of reality originates from the energy of nothingness. Regular matter, stars, worlds, vapor, everything visible contributes less than 5%. This discovery revolutionized cosmology. The vacuum isn't a passive arena where events unfold, it's an active agent shaping cosmic evolution. It bends space-time. It influences light's trajectories. It determines whether the universe will expand perpetually or eventually collapse. The measurements have been refined through multiple satellites and telescope surveys. The Planck satellite charted temperature fluctuations in the cosmic microwave background and verified the dark energy quantity with incredible exactness. Ground-based telescopes measured how galaxies cluster and discovered perfect concordance. Independent techniques converge on identical conclusions. Empty space wields power, real, quantifiable, universe-shaping power, and this raises a staggering question. If vacuum energy can dominate the entire cosmos today, what could it have accomplished in the first instance of creation? The answer leads us to the most crucial event that unfolded before our bang. Everything you've been taught about the Big Bang requires revision. The hot, compressed fireball that forged atoms and released illumination across space was not the origin. It was the consequence of something else, an occurrence called cosmic inflation. Inflation theory, developed during the early 1980s by physicists including Alan Guth and Andre Linde, describes a phase of exponentially rapid expansion that occurred before the conventional bang. During inflation, the universe doubled in dimension repeatedly in an incomprehensibly brief interval. We're discussing expansion exceeding light velocity, surpassing anything physical statutes normally permit. Here's the key point validated through observation. Inflation resolves problems the standard bang model cannot. The universe demonstrates remarkable uniformity. Galaxies separated by billions of light-years possess identical temperature, identical density, identical properties. How did regions of space that could never have communicated become so alike? The old model had no response. Inflation supplies 1. If the universe initiated much tinier than anticipated, then inflated to enormous dimension in a fraction of a second, those distant regions were once proximate enough to achieve equilibrium. They were neighbours. Then inflation stretched them across opposite edges of the observable cosmos. The proof originates from the cosmic microwave background, ancient illumination released 380,000 years after our bang. When scientists charted this radiation across the heavens, they discovered minuscule temperature variations matching inflation forecasts with stunning precision. The configuration of warm and cool zones appears exactly like what you'd obtain if quantum fluctuations during inflation were stretched to cosmic proportions and imprinted on space itself. But here's what makes inflation revolutionary for comprehension. Before it occurred, the universe was frigid and vacant, not scorching and compressed. The inflationary epoch was propelled by vacuum energy, the identical type we discussed earlier. This vacuum energy caused space to expand exponentially, doubling the universe's dimension every microscopic fraction of a second. Think about a chessboard with coins doubling on each square. 1 coin, then 2, then 4, then 8. By the 40th square you'd possess billions. Inflation involved at minimum 80 doublings, possibly hundreds. A region smaller than a citrus fruit expanded to a dimension larger than the observable universe, all in less duration than light requires to traverse an atomic nucleus. When inflation terminated, the vacuum energy powering it didn't simply vanish, it transformed. The energy dumped into space, generating a deluge of particles and radiation. This transformation was the bang you know. The heat, the compression, the primordial soup of substance, all originated from the decay of the inflationary vacuum, so the chronology appears thus. First, cold vacuum energy, then exponential inflation. Then the energy converts to matter and heat. That's the bang you've heard about. Inflation preceded it. The question becomes sharper now. What magnitude of expansion are we describing? Numbers can deceive. When scientists state the universe doubled 80 times during inflation, it sounds almost modest. It's not. Each doubling multiplies dimension by 2. 80 doublings mean multiplying by 2 raised to the 80th power. Write that figure out and you obtain something with 24 digits. The universe expanded by a factor of 1 septillion, or even more depending on inflation's duration. This transpired in approximately 10 to the negative 35 seconds, a decimal point followed by 34 zeros and then a 1. Human cognition isn't constructed to grasp this. Let's attempt an analogy. Imagine a virus particle so minute you'd require an electron microscope to perceive it. Inflate it through 80 doublings and it becomes vaster than the entire observable universe. That's the expansion scale we're examining. What renders this scientifically credible is that it resolves genuine observed problems. One is termed the flatness problem. Space can curve like a sphere's surface, or curve like a saddle or be perfectly flat. Measurements reveal our universe is extraordinarily flat. So flat that if you discharged a laser beam across the observable cosmos, it would journey in an almost perfectly straight trajectory for 93 billion light years. The old model couldn't explain this. Minuscule deviations from flatness in the early universe should have grown enormous over billions of years. We should inhabit a universe that curves dramatically. We don't. Inflation resolves this by stretching space so extensively that any initial curvature got smoothed away. It's like inflating a balloon. The surface becomes flatter and flatter as it expands. Another problem is the horizon problem. Illumination has only possessed 13.8 billion years to travel since our bang commenced. That means regions of space separated by more than that distance have never been in contact. Yet when we measure their properties, they're identical. Same temperature, same expansion rate, same physical statutes. How did they coordinate? Inflation answers this. Those distant regions were once close together, in contact, able to reach the same condition. Then inflation separated them faster than light could reconnect them. The coordination happened before inflation, and the uniformity we observe today is the preserved memory of that earlier contact. The proof supporting these 80 doublings keeps growing stronger. Satellite missions have charted the cosmic microwave background with incredible detail. The configuration of fluctuations matches inflation forecasts to a precision that stunned researchers. Alternative frameworks that don't invoke inflation fail to reproduce what we witness. Scientists calculate that inflation must have persisted long enough for at minimum 80 doublings, possibly thousands more. The precise figure remains uncertain, because we can only perceive the effects within our observable universe. Inflation might have stretched space far beyond what we can detect, generating regions forever concealed beyond our cosmic horizon. This means the universe you can perceive, every galaxy, every star cluster, every bit of illumination, represents just one microscopic patch of a vastly larger reality, and it all originated from a cold, empty vacuum expanding faster than physics should allow. What powered this impossible expansion? For decades, popular science portrayed our bang as the instant when time, space, and substance sprang into being from nothingness. That portrait is obsolete. Contemporary cosmology narrates a different story. Our bang was not a genesis event. It was a transformation. Specifically, it was the instant when the energy driving cosmic inflation converted into matter and radiation, flooding the universe with heat and particles. Conceive of it as a phase transition, analogous to water becoming steam, except far more violent and fundamental. This comprehension originates from matching theory to observation. The cosmic microwave background radiation displays what the universe resembled 380,000 years after our bang. It's a nearly uniform glow with minuscule temperature variations, exactly what you'd anticipate if the universe was once much hotter and denser, then expanded and cooled. But here's the critical insight. If we trace that expansion backward through time using Einstein's equations, we don't reach a genuine origin. We reach a barrier, a point where physics breaks down because temperatures and densities become too extreme for current theories to describe accurately. Scientists label this breakdown a singularity, but it's more honest to call it the edge of our knowledge. Inflation changes this portrait completely. Instead of time commencing at the singularity, time existed beforehand. During the inflationary phase, the universe was frigid and vacant, filled only with vacuum energy. Clocks ticked, space expanded. Cause and consequence operated normally, then inflation ceased, and that's when our bang transpired. The energy that had been locked in the vacuum condition during inflation needed to go somewhere. Physical statutes require energy conservation, so as inflation halted, the vacuum energy decayed. It transformed into elementary particles, quarks, electrons, photons, neutrinos. These particles carried enormous kinetic energy, making them move at nearly light velocity. Their collisions generated heat, vast heat. Within the first second after this transition, the universe reached temperatures of 10 billion degrees Celsius, hot enough to prevent atoms from forming, hot enough that only the most fundamental particles could exist. This seething plasma of matter and energy is what we term the early Bang universe. But that heat wasn't present during inflation. Inflation was frigid. The distinction is crucial. Our Bang wasn't the commencement, it was the warm-up that came after. Scientists have traced this transition using both theoretical calculations and experimental data. Particle accelerators like the Large Hadron Collider recreate early universe conditions by smashing protons together at enormous energies. These experiments confirm how matter behaves at extreme temperatures and validate the equations cosmologists use to model our Bang. The timeline now appears clear. First a cold quantum vacuum, then inflation stretches it exponentially, then the inflationary energy transforms into heat and particles. That transformation is the Bang. After that comes the story you already know: cooling, atom formation, star birth, galaxy assembly. So when did time actually commence? We're not certain yet. Possibly during inflation, possibly before. The honest answer is that we've pushed the boundary of the unknown backward, but we haven't eliminated it. And the evidence for all this gets even stronger. There's a smoking gun in the data proving the universe existed before the traditional Bang. It's concealed in measurements of the cosmic microwave background, and it's termed super-horizon fluctuations. Here's what that signifies. The cosmic horizon is the maximum distance illumination could have travelled since our Bang began. It establishes a limit on how far information can propagate through the universe. Regions beyond this horizon have never been in contact with each other. They're causally disconnected. The standard Bang model forecasts that temperature variations in the cosmic microwave background should only exist on scales smaller than this horizon. Anything larger than the horizon represents regions that never interacted, so they shouldn't display coordinated configurations. But that's not what we witness. The data reveals fluctuations on scales larger than the cosmic horizon, much larger. These super-horizon features appear in multiple independent measurements taken by the WMAP satellite, the Planck satellite, and ground-based telescopes. The evidence is undeniable. How do you obtain coordinated configurations across regions that have never communicated? There's only one explanation. Those regions were in contact before our Bang. During inflation, when the universe was minuscule and frigid, quantum fluctuations occurred across all space. These fluctuations became the seeds of structure. Then inflation stretched those fluctuations to enormous dimensions, far larger than the cosmic horizon. When our Bang happened and hot matter filled the universe, these inflated quantum configurations were already imprinted on space. They manifested as temperature variations in the primordial plasma. We perceive those variations today as warm and cool zones in the cosmic microwave background. The mathematics is exact. Inflation forecasts a particular configuration of correlations between temperature and polarization in the cosmic microwave background. It forecasts how the magnitude of fluctuations should vary with scale. It forecasts the spectrum of these variations should be nearly but not perfectly uniform across different dimensions. Observations match these forecasts with extraordinary precision. During 2003, the WMAP team published the first high-precision measurements displaying the forecast correlation configuration, including features on super-horizon scales. The non-inflationary Bang model forecast something entirely different. The data eliminated the old model and validated inflation. 20 years later, with even superior instruments, the agreement has only improved. The Planck satellite charted these fluctuations with such exactness that scientists can now test inflation's forecast to fractions of a percent. Every test passes. The super-horizon correlations are exactly where they should be. This represents one of the strongest pieces of proof in all cosmology. The configurations we perceive in the heavens could not exist if our Bang was the origin. They require a prior phase, inflation, where the universe was smaller, colder, and governed by different physics. Contemplate what this signifies. We've moved beyond philosophical speculation about before the Bang. We possess observational proof. The illumination from the ancient universe carries information about circumstances that existed before the traditional Bang transpired. We can measure properties of that pre-bang condition. We can test frameworks about it. The universe keeps secrets, but it also leaves clues. The cosmic microwave background is the oldest illumination in the universe, released 380,000 years after our bang. It's been travelling through space for over 13 billion years. When we capture this ancient radiation with telescopes, we're perceiving a snapshot of the cosmos when it was young, hot, and simple. But concealed within that snapshot is information from even earlier, from the inflationary epoch before our bang. Here's how that operates. During inflation, the vacuum energy dominating the universe possessed quantum properties. Like everything in quantum mechanics, it experienced random fluctuations. These weren't just microscopic ripples. Inflation amplified them, stretching microscopic quantum jitters into variations spanning millions of light years. When inflation concluded and the bang transition occurred, those variations became imprinted on the distribution of matter and energy. Regions with marginally more density would eventually form galaxy clusters. Regions with marginally less density would become cosmic voids. The structure of the entire universe traces back to quantum randomness during inflation. The cosmic microwave background captures this information because the photons released 380,000 years after our bang travelled through space that already possessed these density variations. Warm zones in the radiation originate from regions that were slightly denser. Cool zones originate from regions that were less dense. The configuration we perceive today is a fossilized chart of circumstances generated during inflation. Scientists have measured this chart with incredible detail. The temperature varies by only a few parts per 100,000. The universe was remarkably uniform even then, but within that uniformity lies structure. Particular dimensions of warm and cool regions appear more frequently than others, generating what cosmologists term the power spectrum. Inflation makes exact forecasts about what this power spectrum should resemble. The distribution of fluctuation dimensions should follow a nearly scale invariant configuration, meaning fluctuations of different dimensions possess almost the same amplitude. Observations validate this forecast. The match is so close that it's become one of the fundamental pillars of contemporary cosmology. But the cosmic microwave background reveals more than just density variations. It also carries information about polarization, the orientation of the electromagnetic waves. This polarization gets influenced by gravitational waves, and inflation should produce gravitational waves as a byproduct of its exponential expansion. Detecting these primordial gravitational waves remains one of cosmology's biggest objectives. If discovered, they would supply direct proof of inflation's energy scale and offer a window into physics at temperatures far beyond what particle accelerators can reach. Multiple experiments are searching for this signal right now. Even without detecting gravitational waves yet, the temperature and polarization data we already possess constrains inflation frameworks. Some models forecast large gravitational wave signals. Those models are now ruled out. Other models forecast particular configurations in how fluctuations behave on different scales. Observations test those forecasts and eliminate models that don't match. The cosmic microwave background has become a laboratory for examining the pre-bang universe. Every improvement in measurement technology brings fresh insights. The data keeps improving, and the portrait of inflation keeps getting clearer. What it reveals is a universe that existed in a condition completely different from anything we experience today. We presume time flows in one direction, from past to future. We remember yesterday but not tomorrow. Causes precede consequences. The sequence of instants feels fundamental to reality. But what if time itself only commenced during inflation or even later? This isn't wild conjecture. It originates from taking Einstein's general relativity seriously. Einstein demonstrated that time and space are linked as spacetime, a four-dimensional fabric that can bend, stretch, and warp. Gravity isn't a force acting through space and time. Gravity is the curvature of space-time itself. This means time is physical. It's part of the universe, not something external that the universe exists within. And if time is physical, then asking what transpired before the universe existed might be like asking what's north of the North Pole. The question presumes a framework that doesn't apply. Stephen Hawking explored this notion using quantum mechanics. In collaboration with James Hartler, he proposed the no-boundary hypothesis. The mathematics describes the universe's genesis using something termed imaginary time, a concept from quantum theory where time behaves like a spatial dimension. In this framework, the universe doesn't possess a beginning point. Instead, it smoothly transitions from a timeless quantum condition into the classical space-time we experience. Consider Earth's surface. If you journey south, you eventually reach the South Pole. You can't proceed farther south because there is no farther south. You've reached the limit. The no-boundary proposal suggests something analogous for time. Trace cosmic history backward, and you eventually reach a boundary where time itself curves back on itself. There's no before because time doesn't extend in that direction. This generates a peculiar portrait. The universe is finite in time but possesses no beginning instant. It's self-contained. No creator needed, no violation of causality, no infinite past to explain. Other physicists disagree. Julian Barber argues that time is an illusion emerging from the changing configurations of matter. According to his view, only the present instant exists. The past is a memory stored in the current arrangement of particles. The future hasn't transpired yet, so it doesn't exist. If time is illusory, then asking about before our bang becomes meaningless in a different fashion. The confusing aspect is that both perspectives might be partially correct. At everyday scales, time behaves as we anticipate. Clocks tick. Causes produce consequences. The arrow of time points clearly forward. But at the quantum scale governing the universe's genesis, time becomes fuzzy and uncertain, just like position and momentum. During inflation, if it occurred, time likely existed in a conventional sense. The vacuum energy condition could persist for a duration. Space could expand over time. But before inflation, that's where our comprehension fails. The mathematical singularity at the commencement of time might be telling us that general relativity breaks down and a quantum theory of gravity is needed. Nobody has successfully combined quantum mechanics and general relativity into a complete theory yet. Without that theory, questions about the ultimate origin remain open. We can trace cosmic history back to the Planck time, 10 to the negative 43 seconds after our bang. Earlier than that, our physics doesn't operate. What does before even signify in that regime? Language fails us when discussing the genesis of time. Every word we use presumes time already exists. Before implies an earlier instant. Cause implies something happening first. Beginning suggests a transition from not existing to existing. But if time itself emerged with the universe, these concepts collapse into paradox. Cosmologists wrestle with this constantly. They need to communicate notions that transcend normal experience using words constructed for normal experience. The result can sound contradictory or confusing, but the confusion originates from the limits of language, not necessarily the limits of reality. One approach is to abandon the notion of before entirely. Georges Lemaitre, the Belgian priest and physicist who first proposed cosmic expansion, suggested the universe commenced in a day without yesterday. St. Augustine made a comparable argument 1600 years earlier, claiming time was generated along with the universe, so asking what came before is nonsensical. Contemporary physics supplies a framework for this. General relativity describes space-time as a manifold, a mathematical structure with definite boundaries. Time could possess a boundary at our bang, just as Earth's surface possesses a boundary at the poles. Asking what's before the boundary is like asking what colour is Tuesday. The question contains a category error. But here's where it gets intriguing. Quantum mechanics might allow an escape from this conclusion. In quantum theory, particles can tunnel through barriers they shouldn't be able to cross. Electrons tunnel through insulators. Alpha particles tunnel out of atomic nuclei. It's a thoroughly validated phenomenon. Some physicists propose the universe itself tunneled into existence from a quantum vacuum condition. Alexander Vilenkin developed this notion in detail. He describes a scenario where a universe with zero dimension possesses some small quantum probability of tunneling into a condition with non-zero dimension. Once it makes that transition, inflation takes over and expands it to cosmic proportions. In this portrait, there is no before in the usual sense. But there is a prior quantum condition, the vacuum from which the universe tunneled. Time commences when the universe achieves classical space-time properties, but the quantum condition exists outside of time as we comprehend it. David Bohm's pilot wave interpretation of quantum mechanics offers another perspective. In Bohm's framework, particles possess definite positions at all times, guided by a quantum potential. When applied to cosmology through the Wheeler-DeWitt equation, this suggests the universe could possess definite properties even at the instant of genesis. The quantum potential acts like an effective cosmological constant driving the initial expansion. These notions remain theoretical, but they point toward a resolution. Maybe before our bang doesn't signify earlier in time. Maybe it signifies prior in some other sense, causally prior, logically prior, or quantum mechanically prior. The condition from which the universe emerged wouldn't exist at an instant before time commenced. It would exist outside the framework of time altogether. This challenges our intuition deeply. We're accustomed to thinking of existence as happening in time, but quantum conditions don't necessarily exist in time. They exist in configuration space, an abstract mathematical realm describing all possible conditions a system could occupy. The universe's emergence could be a transition from one configuration to another, with time itself being a feature that emerges during the transition. Philosophers have argued about these questions for millennia. Physics now provides us tools to make those arguments exact, testable, and grounded in observation. We may never possess a complete answer, but we're asking superior questions. And some frameworks go even farther. What if our universe wasn't born from nothingness but from a collision? What if everything we perceive originated from two massive structures smashing together in a higher dimension? This is the ekpyrotic model, and it's constructed on serious mathematics. The framework emerges from string theory, a framework that describes particles as minuscule vibrating strings rather than point-like objects. String theory requires extra dimensions beyond the three of space and one of time we experience. These dimensions could be curled up small, or they could be large but concealed from our direct perception. In some versions of string theory, our universe exists on a three-dimensional membrane, or brain, floating in higher dimensional space. Consider a sheet existing in a three-dimensional room. We're trapped on the sheet, unable to move off it, while the room contains other dimensions we can't access. The ekpyrotic model, proposed in 2001 by physicists including Paul Steinhardt and Neil Turok, suggests there are two such brains parallel to each other. An attractive force pulls them together over vast spans of time. They approach slowly, then they collide. The collision releases enormous energy. From our perspective, trapped on one brain, this would resemble our bang. Matter and radiation flood our three-dimensional space. The universe heats up, expands, cools, and evolves into the cosmos we observe today. But it wasn't a beginning. It was a crash. This framework resolves several problems that inflation struggles with. It explains why the universe is flat and uniform without requiring exponentially rapid expansion. The slow approach of the brain smooths out any irregularities before impact. It explains the configuration of fluctuations in the cosmic microwave background as vibrations generated by the collision, and it avoids the multiverse problem plaguing inflationary models. Inflation, if it persists long enough, produces an infinite quantity of pocket universes with random properties. This makes the framework hard to test, because any observation can be explained as we just happen to inhabit this pocket. The ekpyrotic model doesn't possess this issue. One collision generates one universe with predictable properties, but the ekpyrotic scenario faces challenges. Nobody fully comprehends what transpires during a brain collision. String theory isn't developed enough yet to precisely calculate the outcome. Some critics argue the collision might destroy the smoothness the model depends on. Others point out that obtaining the correct spectrum of density fluctuations requires fine-tuning the collision parameters. Despite these difficulties, the ekpyrotic model remains scientifically viable. It makes testable forecasts. And for instance, it forecasts gravitational waves from the collision would be too weak to detect in the cosmic microwave background. Inflation forecasts they might be detectable. Future observations could distinguish between these scenarios. The ekpyrotic model also connects to something deeper, the notion that our bang wasn't unique. If brains can collide once, they can collide multiple times. The collision could bounce the brains apart. They'd separate, drift in the higher dimension, then get pulled back together by the attractive force. Another collision, another bang. This leads to a cyclic cosmology where the universe traverses endless cycles of collision and separation. Each cycle generates a cosmos. Each cycle concludes when the branes separate. Then the process repeats. From our perspective, it would appear like the universe expands, then contracts, then bounces into a new expansion. Except the bounce transpires through a collision in a higher dimension, not a simple reversal of our three-dimensional space. The implications are staggering. The singularity at the commencement of our bang has haunted physics for decades. A point of infinite density, infinite temperature, infinite curvature, a location where equations break down and give nonsensical answers. Most physicists don't believe the singularity is genuine. They perceive it as a sign that general relativity fails under extreme circumstances. The Big Bounce framework offers a solution. Instead of the universe commencing at a singularity, it transitions smoothly from a contracting phase into our current expanding phase. The bounce transpires at a finite, though extremely high, density. No infinities. No breakdown of physics. This isn't just wishful thinking. It's grounded in loop quantum gravity, an approach to combining quantum mechanics and general relativity. In loop quantum gravity, space itself possesses a discrete structure at the tiniest scales, like pixels on a display. When you attempt to compress matter and energy into an infinitely small point, the quantum properties of space prevent it. There's a minimum volume. A bounce becomes inevitable. Calculations using loop quantum gravity demonstrate that a collapsing universe would reach a maximum density, then rebound into expansion. The mathematics is intricate, but the conclusion is clear. Quantum effects generate a repulsive force at extreme densities that overwhelms gravity. Consider it like compressing a spring. Push too hard and it pushes back. Recent work published during 2020 by Robert Brandenberger and Jiwei Wang explored how a bounce could produce the observed features of our universe. They discovered that if the pre-bounce universe underwent a phase of slow contraction, analogous to inflation but in reverse, it could generate the same configuration of density fluctuations we perceive in the cosmic microwave background. This signifies the universe before the bounce might have resembled ours in reverse. Galaxies merging instead of separating, illumination shifting toward blue instead of red, time running backward from our perspective, though forward from the perspective of observers inhabiting that epoch. When the bounce occurred, information from the pre-bounce universe could have survived the transition. The fluctuations in matter and energy distributions would carry through, seeding structure in the post-bounce cosmos. This generates a radical portrait. Our bang wasn't the start, it was the midpoint of a much longer story. Before our expansion came a contraction. Before that, possibly another expansion. The universe might be far older than 13.8 billion years. It might possess no age at all, stretching infinitely into the past through endless cycles. The Big Bounce avoids many philosophical problems plaguing creation from nothing scenarios. It doesn't require explaining why the universe exists rather than nothing. It doesn't require an instant when time commences. It simply requires quantum gravity to behave the fashion loop quantum gravity forecasts. Testing this framework is challenging. The bounce itself transpired under circumstances we can't reproduce in laboratories, but the framework makes forecasts about the cosmic microwave background and the spectrum of gravitational waves that might be detectable. Several experiments are searching for these signatures. If the Big Bounce is correct, then the question shifts. We don't need to explain the universe's genesis. We need to explain its structure and its cycles, which brings us to the most ambitious notion yet. Imagine a cosmos that never commenced and never concludes. A universe caught in an eternal rhythm of expansion, contraction, bounce, and expansion again. Each cycle lasting trillions of years. Each cycle generating the circumstances for stars, worlds, and possibly life. This is cyclic cosmology. The notion isn't new. Ancient Stoic philosophers proposed an eternal cycle of cosmic genesis and destruction they termed ekpyrosis. Hindu cosmology describes analogous cycles over vast timescales, but contemporary physics puts these concepts on firm mathematical ground. In the cyclic model, developed by Paul Steinhardt and Neil Turok, dark energy plays a crucial role. Remember, dark energy is the mysterious component causing our universe's expansion to accelerate. In their model, Dark energy eventually pushes galaxies so far apart that the universe becomes essentially vacant. Matter gets diluted to negligible density. Stars burn out. Black holes evaporate through Hawking radiation over incomprehensible time spans, but the dark energy doesn't disappear. It continues to exist, and in the ekpyrotic cyclic model, it acts as a bridge to the next cycle. The same attractive force between brains that caused our bang collision continues to operate. Over trillions of years, it pulls the brains together again. Another collision occurs, another bang erupts, a new universe commences. Crucially, each cycle doesn't produce identical circumstances. The universe grows larger with each iteration. The scale factor, a measure of cosmic dimension, increases exponentially from cycle to cycle. Entropy builds up, but it gets diluted by the expansion. The second law of thermodynamics isn't violated because the universe keeps becoming bigger, giving entropy more room to disperse. This resolves the entropy problem that killed earlier cyclic models. During the 1930s, physicist Richard Tolman demonstrated that a naively cyclic universe would accumulate entropy until it couldn't bounce anymore. The Steinhardt-Turok model avoids this by incorporating dark energy and allowing the universe to expand net over many cycles. Another cyclic proposal originates from Roger Penrose, the Nobel laureate mathematician. His conformal cyclic cosmology suggests the universe expands forever until all matter decays into radiation. At that point, nothing remains with rest mass. Everything moves at light velocity. When nothing possesses mass, the concepts of time and distance become meaningless. Penrose argues this massless condition can be mathematically mapped onto a new bang. The infinite future of one universe becomes the bang of the next. It's conformal because the geometry is preserved under this transformation, even though scales change. Time becomes circular or perhaps spiral. These models remain speculative, but they're testable. They forecast particular configurations in the cosmic microwave background. Some versions forecast we might perceive circular configurations from collisions in the previous cycle, like ripples on a pond imprinted in the radiation. Searches have been conducted. So far, no definitive signals discovered. But the search continues. Cyclic cosmology offers philosophical appeal. It removes the awkward question of why the universe exists. It always has existed and always will, changing form but never truly commencing or concluding. Existence becomes fundamental, while particular configurations like our current expanding universe become temporary phases. But it also raises fresh questions. If cycles repeat forever, have there been infinite cycles? Does the universe possess a memory of earlier cycles? Are the physical statutes the same in each cycle? Or do they evolve? We may be on the verge of answering some of these questions. Here's a possibility sounding like fiction, but emerging from serious theoretical work. Each cycle of the universe might operate under different physical statutes. The constants governing particle masses, force strengths, and cosmic behavior could shift from one cycle to the next. Why would this transpire? In many theoretical frameworks, the values of physical constants aren't established by fundamental principles. They're environmental, determined by how quantum fields settle into their lowest energy conditions. It's like water freezing. The exact configuration of ice crystals depends on random fluctuations during the freezing process. During a bounce or brane collision, the extreme energies could reset these fields. As the new universe expands and cools, the fields would settle into new configurations, different constants, different physics, a cosmos that appears and behaves differently from ours. This carries profound implications. In most cycles, the constants might not allow complex structures to form. Galaxies wouldn't assemble, stars wouldn't ignite, chemistry might not exist. Those universes would be sterile, simple, and short-lived. But occasionally, by random chance, the constants would align just right. Atoms could form, complexity could emerge, life might evolve. We find ourselves in one of those rare successful cycles because we couldn't exist in any other kind. This is a version of the Anthropic principle, the observation that the universe must be compatible with the conscious life that observes it. In a cyclic multiverse where each cycle possesses different physics, the Anthropic principle explains our particular set of constants without requiring fine-tuning. Some physicists find this explanation unsatisfying. It replaces the mystery of why our constants possess life-permitting values with the assumption that all possible values occur somewhere in the cyclic sequence. You haven't really explained anything. You've just moved the mystery one level deeper. Others embrace it. If the cyclic model is correct and constants vary between cycles, then we can make statistical forecasts. We should find ourselves in a typical life-permitting cycle, not a maximally life-permitting one. Our universe should be close to the boundary where complex structures barely form. Too far from the boundary would be statistically unlikely. Some proof tentatively supports this. The cosmological constant in our universe sits uncomfortably close to the maximum value that would allow galaxies to form. Much larger and cosmic expansion would have accelerated so rapidly that matter could never clump together. Much smaller, and we'd need to explain why it's not exactly zero. We seem to be near a boundary, which cyclic anthropic reasoning forecasts. Testing whether constants varied in previous cycles is nearly impossible. The bounce erases most information, but some frameworks suggest subtle imprints might survive. Topological defects, certain kinds of knots in spacetime could potentially persist through a bounce and leave detectable traces. More realistically, we can test whether the framework allowing variable constants makes sense. String theory, for instance, forecasts a vast landscape of possible vacuum conditions, each with different effective physical statutes. Exploring which of these conditions are accessible and how transitions between them might occur is active research. The big portrait emerging from cyclic cosmology, with variable physics, is humbling and grand simultaneously. Our universe isn't special. It's one outcome of an eternal process that generates cosmos after cosmos, most of them failures, some of them interesting, a few of them giving rise to observers who can ask these questions. We're left with a vision of reality far stranger than the simple, something from nothing narrative. There might be no ultimate commencement, no final conclusion, no single set of physical statutes. Just an infinite churning of possibilities, with brief windows where complexity flourishes before collapsing back into simplicity, then re-emerging in a new form. The universe, in this view, is not a creation but an eternal transformation. General relativity and quantum mechanics are the two pillars of contemporary physics. General relativity describes gravity, black holes, and cosmic expansion. Quantum mechanics governs atoms, particles, and the microscopic world. Both frameworks operate brilliantly in their domains, but they contradict each other at extreme scales. Loop quantum gravity attempts to resolve this conflict by applying quantum principles to space and time themselves. Instead of treating space as a smooth continuum, loop quantum gravity describes it as a network of discrete loops, microscopic quantum units connected like chainmail. At normal scales, this discrete structure averages out and space appears smooth. Just like a television display appears continuous from a distance but is actually made of pixels. The key insight arrives when you apply these notions to the Bang singularity. In classical general relativity, matter collapses to infinite density. But loop quantum gravity states space possesses a minimum volume. You can't compress something smaller than the fundamental quantum unit of space, which exists at the Planck scale, about 10 to the negative 35 meters. When a collapsing universe reaches this density, quantum repulsion activates. The mathematics demonstrates that gravity effectively reverses, becoming repulsive instead of attractive. The collapse halts and reverses into an expansion. The singularity gets replaced by a bounce, a smooth quantum bridge connecting contraction to expansion. This isn't conjecture. Scientists have performed detailed calculations using loop quantum gravity equations. They've simulated how a universe evolves through the bounce. The results demonstrate that cosmological perturbations, the minuscule fluctuations seeding galaxies, can propagate through the bounce without being destroyed. Information survives the transition. Abhay Ashtekar and his collaborators at Penn State have led much of this research. They've demonstrated that a pre-bounce universe undergoing slow contraction would generate a nearly scale-invariant spectrum of perturbations, matching what we witness in the cosmic microwave background. The bounce doesn't erase this structure, it preserves it. This generates a testable forecast. Loop quantum gravity bounces should produce particular signatures in gravitational waves. The spectrum should differ slightly from what inflation forecasts. As gravitational wave detectors become more sensitive, they might distinguish between these scenarios. There's also a philosophical shift here. loop quantum gravity doesn't require anything beyond known physics. It doesn't invoke extra dimensions, colliding brains, or exotic forms of matter. It simply takes quantum mechanics seriously at all scales, including spacetime itself. The singularity that terrified physicists for decades disappears. It was never genuine, just an artifact of using classical equations where they don't apply. Once you account for quantum effects, the universe possesses no beginning or conclusion in the traditional sense. It's a continuous process with phases of expansion and contraction connected by quantum bridges. This resolves the paradox of creation. You don't need to explain how something originated from nothing because there was never nothing. There was always a quantum spacetime structure, eternally transforming between different conditions. But what triggered our particular phase? One of the strangest notions in cosmology, sounds like circular logic but might be genuine. The universe could have generated the circumstances that allowed it to exist. It bootstrapped itself into reality through a self-consistent loop. Here's how this operates. In quantum mechanics, the future can influence the past through what's termed retrocausality. When you measure a particle's condition, you don't just observe what it is, you retroactively determine what it was. The act of measurement reaches backward through time and selects which possibility becomes genuine from a cloud of quantum probabilities. John Wheeler, one of the great physicists of the 20th century, proposed the universe might operate the same fashion. He termed it the participatory anthropic principle. The existence of observers who can measure and comprehend the universe contributes to bringing that universe into existence. The cosmos generates observers who look back at its genesis, and through that observation help define what the genesis was. This sounds mystical, but it emerges naturally from certain interpretations of quantum mechanics. The universe's wave function describes all possible configurations it could possess. When conscious observers emerge and begin making measurements, they collapse parts of this wave function, selecting which history actually occurred. In this view, our bang wasn't just a random occurrence. It was the only occurrence consistent with a universe that would eventually produce observers. Other possible initial circumstances might have led to sterile universes with no complexity. Those branches of the wave function never got actualized because no observers existed to collapse them into reality. This generates a causal loop. The universe exists in a form that allows observers. The observer's existence retroactively selects the initial circumstances that led to them. The initial circumstances cause the observers. The loop is self-consistent. Physicist James Hartle has explored these notions mathematically. His work with Stephen Hawking on the no-boundary proposal incorporates this self-selection principle. The universe doesn't possess a single fixed past. It possesses a superposition of possible pasts, and the act of existing in the present helps determine which past becomes genuine. Other frameworks reach analogous conclusions through different routes. In Lee Smolin's cosmological natural selection, universes that produce black holes generate baby universes through quantum tunneling. Each baby universe possesses slightly different physical constants. Over many generations, this process selects for universes optimized to produce black holes, which also happen to be effective at producing stars, worlds, and complexity. We exist in such a universe not by chance, but because only this type of universe can persist through the selection process. The universe bootstraps its own existence through an evolutionary mechanism spanning across cosmic generations. These notions remain controversial and difficult to test, but they point toward a resolution of the deepest mystery. Why is there something rather than nothing? The answer might be that nothing is unstable in a quantum framework. Any fluctuation that generates something which can sustain itself will persist. Others collapse. We observe a self-sustaining configuration because non-sustaining ones don't produce observers. The universe exists because it can exist. The circumstances making it possible are the circumstances it selects for through its own evolution. Reality is a strange loop that generates itself, and the mathematics describing this gets even stranger. We experience 3 dimensions of space: left, right, forward, backward, up, down. Add time and you obtain 4 dimensions. String theory states there are at minimum 7 more concealed dimensions, giving a total of 11. Why haven't we noticed them? The framework proposes they're compactified, curled up so minuscule that we can't perceive them. Imagine an ant walking on a telephone wire. From far away, the wire appears one-dimensional, The ant can only move forward or backward, but up close the wire possesses thickness. The ant could walk around its circumference, exploring a second dimension we initially missed. The extra dimensions in string theory operate similarly. They exist at every point in our three-dimensional space, but they're rolled up at scales far tinier than atoms. Particles can vibrate through these concealed dimensions, and different vibration configurations appear to us as different particle types. An electron is one vibration mode, a quark is another. Photons, neutrinos, everything emerges from strings vibrating through this higher dimensional space. This framework carries profound implications for cosmology. Our universe might be a three-dimensional surface embedded in this higher dimensional space. Everything we perceive, stars, galaxies, illumination, is trapped on this surface. But gravity is different. Gravitational effects can leak into the extra dimensions, which might explain why gravity is so much weaker than the other fundamental forces. The ekpyrotic model we discussed earlier exploits this. If parallel three-dimensional branes exist in the higher dimensional bulk, and if they can move through those extra dimensions, then collisions become possible. Our bang would be the aftermath of such a collision, with the pre-collision condition existing in this higher dimensional framework. String theory also suggests that different compactifications of the extra dimensions produce different physical statutes. There might be 10 to the 500th or more distinct fashions to curl up the extra dimensions, each generating a different vacuum condition with different particle masses and force strengths. This vast landscape of possibilities connects to the notion of varying constants between cosmic cycles. Testing these notions is extraordinarily difficult. The energies needed to probe the extra dimensions directly exceed anything achievable in particle accelerators by many orders of magnitude. But indirect proof might exist. Gravitational waves propagating through the bulk could carry signatures of extra dimensions. Minuscule deviations in how gravity behaves at small scales might reveal the geometry of concealed dimensions. Experiments at the Large Hadron Collider searched for signs of extra dimensions by looking for missing energy in particle collisions. If particles escaped into the bulk, energy would seem to disappear. So far, no definitive signals. But the search continues at higher energies and with greater exactness. String theory remains incomplete and controversial. Some physicists embrace it as the best candidate for a theory of everything. Others criticize it for making few testable forecasts and requiring fine-tuning to match observations. The debate continues, but the core insight persists. The universe we observe might be a shadow of a larger reality. The three dimensions of space we navigate might be an illusion, a projection of something far more intricate existing in realms we can't directly access. This raises a question about the pre-bang condition. If extra dimensions exist, what role do they play in the universe's genesis? Inflation was supposed to be a one-time occurrence, a brief phase of exponential expansion that established our bang, then concluded. But the mathematics suggests something far stranger. Once inflation initiates, it might never completely halt. Here's why. Inflation is propelled by a quantum field termed the inflaton. When this field sits at a high energy value, space expands exponentially. As the field rolls down toward lower energy, inflation slows and eventually stops. The field's energy converts to matter and radiation. That's the bang we know, but quantum fluctuations influence the inflaton field just like they influence everything else. In some regions of space, random fluctuations push the field back up to higher energy before it can finish rolling down. Those regions keep inflating. Meanwhile, other regions successfully conclude inflation and produce hot bang circumstances. This generates a fractal structure. Our observable universe is a pocket where inflation concluded. But beyond our cosmic horizon, other regions are still inflating. And within those inflating regions, new pockets constantly form where inflation halts. Each pocket becomes a bang universe. Each one expands, cools, and potentially develops galaxies, stars, and life. The process never concludes. Alan Guth and Andre Lin developed this eternal inflation framework during the 1980s. It's a natural consequence of combining inflation with quantum mechanics. The implications are staggering. There's not one universe. There's a vast, possibly infinite multiverse. Our bang is just one bubble in an endless foam of universes. Each bubble might possess different properties. The quantum fluctuations generating new pockets could also influence the values of physical constants, producing pocket universes with different physical statutes. This resolves some mysteries while generating others. It explains why our universe possesses life-permitting constants. There are infinite universes with all possible constants. We necessarily find ourselves in one compatible with our existence. But it also signifies the framework can't forecast what we should witness, because every possible observation occurs somewhere in the multiverse. Eternal inflation also possesses a past. The Borguth-Vilenkin theorem, proved during 2003, demonstrates that any region of space expanding on average must possess a boundary in the past. Inflation can't be eternal into the past. It must have initiated somehow from some initial circumstance. This brings us back to the Genesis question. What triggered inflation in the first place? The metastable false vacuum, a quantum fluctuation, a prior contracting phase. The theorem doesn't tell us what came beforehand, but it proves there was a beforehand. Some physicists find eternal inflation disturbing. It seems to make science impossible if every outcome exists somewhere. Others argue we can still make probabilistic forecasts by counting which types of observers are most common across the multiverse. The debate is unresolved, but the mathematics of eternal inflation is solid. Unless quantum mechanics or the inflation field behaves very differently than we think, the multiverse seems unavoidable. What does this signify for the concept of nothingness? Stand back and examine the big portrait. If eternal inflation is correct, reality is not a single universe with one bang. It's an infinite collection of disconnected regions, each with its own bang, expanding within an ever-inflating background. Consider it as quantum foam on a cosmic scale. The inflating space is the substance. The pocket universes are bubbles forming within it. Each bubble thinks it's the entire universe because the inflating background expands faster than light, forever concealing other bubbles beyond an unreachable horizon. This structure might be nested. Within each pocket universe, if circumstances allow, new phases of inflation could commence. Those would spawn their own sub-pockets. You'd obtain a hierarchy of nested realities, each level spawning the next, all embedded within the eternal inflation that never halts. Max Tegmark has classified different types of multiverses. Level 1 is simply distant regions of our own universe, beyond our observation horizon, but obeying the same physics. Level 2 is the eternal inflation multiverse we're discussing, different bubbles with potentially different physical constants. Level 3 involves the many worlds interpretation of quantum mechanics, where every quantum measurement splits reality into branches. Level 4 would be completely different mathematical structures obeying different logical rules. The Level 2 multiverse from eternal inflation is the most scientifically grounded. It emerges directly from combining well-tested physics, general relativity, quantum mechanics, and inflation. You don't need to presume anything exotic. The multiverse is a consequence, not a presumption. But it generates an observability problem. We can only perceive inside our bubble. The inflating background between bubbles expands so rapidly that illumination from other bubbles can never reach us. They're not just far away, they're causally disconnected. No information can travel between bubbles. Each pocket universe is fundamentally isolated. This seems to put other bubbles beyond science's reach. If we can't observe them, test forecasts about them, or interact with them in any fashion, are they really scientific entities, or have we crossed into metaphysics? Some argue the multiverse remains scientific because it's a forecast of testable frameworks. We don't test the multiverse directly, we test inflation. If inflation is correct, eternal inflation follows naturally. Rejecting the multiverse signifies rejecting the logical consequences of confirmed physics. Others remain skeptical. They argue that effective scientific frameworks should make definite forecasts about what we witness. The multiverse allows anything, which signifies it forecasts nothing. It's a failure of our frameworks, not a feature of reality. The debate continues, but observationally we're stuck in our bubble. We can examine its properties. We can chart the cosmic microwave background. We can measure the expansion rate and the dark energy density. All of this informs us about our pocket universe. Whether infinite other pockets exist remains unknown, but the mathematics strongly suggests they do, and if they do, then the question of what existed before our bang gets even stranger. Our bang was not the commencement of inflation, it was the conclusion of inflation in our local region. Other regions never stopped inflating. Still others concluded inflation earlier or later. There's no universal before the bang. Each pocket possesses its own timeline, its own genesis, its own history. The multiverse as a whole might be timeless, with pockets commencing and concluding at all instants, embedded in an eternal background. This is the portrait contemporary cosmology paints, not a simple Genesis story, a complex layered reality where our universe is one small piece. For decades, popular science treated the Bang singularity as a physical reality, a point where the universe was infinitely dense, infinitely hot, infinitely curved. But physicists never believed it. A singularity signals the breakdown of your framework, not a description of reality. When equations give infinite answers, they're telling you the mathematical framework no longer applies. You've pushed the model beyond its domain of validity. General relativity forecasts singularities. Black holes possess them at their centers. Our Bang possesses one at its commencement. But general relativity as a classical framework, it doesn't include quantum mechanics. At small scales and high energies, quantum effects become crucial. Ignoring them guarantees your forecasts will fail. Consider it like forecasting the behavior of water. Classical fluid mechanics operates excellently for describing rivers, waves, and pipes. But at molecular scales, where individual water molecules matter, you need quantum chemistry. Classical fluid equations give nonsensical results at atomic scales because they're the wrong tool. General relativity is the wrong tool at Planck scales. The Planck length is 10 to the negative 35 meters. The Planck time is 10 to the negative 43 seconds. The Planck energy is about 10 to the 19 giga-electron volts, roughly the energy of a flying mosquito compressed into a single particle. These are the scales where quantum gravity becomes essential. At these scales, space and time stop behaving classically. They fluctuate. They become uncertain. The very concepts of distance and duration lose their usual meanings. A singularity, which requires compressing something into exactly zero volume, becomes impossible. Quantum mechanics won't allow it. Stephen Hawking and Roger Penrose proved theorems demonstrating that general relativity forecasts singularities under very general circumstances. Their work was brilliant and crucial, but it also highlighted exactly where general relativity fails. The singularity theorems inform us where we need a superior framework. Loop quantum gravity replaces the singularity with a bounce. String theory might replace it with a minimum dimension determined by string length scales. Other quantum gravity proposals possess their own solutions. The details differ. But the conclusion is the same. The singularity isn't genuine. This signifies our Bang wasn't an instant when the universe sprang from nothing into something. It was a transition from one quantum condition to another. The pre-transition condition might have been a contracting universe, an inflating vacuum, a higher dimensional brain configuration, or something else entirely. But it was something, not nothing. The mathematical fiction of the singularity misled generations of physicists and the public. It made the universe's genesis seem more mysterious than it is. Yes, we don't fully comprehend quantum gravity. Yes, the precise details of the transition remain unclear. But we recognize the universe didn't commence at an infinitely dense point because infinite density is unphysical. This shifts the question. We're not attempting to explain how something originated from absolute nothing. We're attempting to explain what the pre-Bang quantum condition was and why it transitioned into our current expanding universe. That's still a profound question, but it's a tractable one. Quantum mechanics and general relativity are both experimentally validated to incredible exactness. Quantum mechanics forecasts the behavior of atoms, lasers, and computer chips with perfect precision. General relativity forecasts the orbits of worlds, the bending of illumination around galaxies, and the detection of gravitational waves. Both frameworks operate flawlessly in their domains, but they contradict each other when you attempt to combine them. This isn't a minor technical issue, it's a fundamental clash of principles. In quantum mechanics, you can measure a particle's energy with arbitrary exactness if you're willing to wait long enough. Time is a background parameter that flows uniformly. In general relativity, time is part of spacetime, which curves and warps. Time runs at different rates depending on gravity and motion. There's no universal clock. In quantum mechanics, particles exist in superpositions. An electron can be in multiple locations at once until you measure it. In general relativity, space-time possesses a definite geometry. You can't possess space-time in a superposition of different curvatures. Or can you? These contradictions become critical at Planck scales, where both quantum effects and gravitational effects are strong. You need a framework of quantum gravity, a framework that incorporates both sets of principles consistently. Nobody possesses one yet that's complete, tested, and universally accepted. String theory offers one approach. It replaces point particles with vibrating strings. This smooths out the singularities plaguing quantum gravity calculations. The mathematics is elegant, and the framework potentially describes all forces and particles within one framework. But it requires extra dimensions, possesses many possible solutions, and makes few testable forecasts at accessible energies. Loop quantum gravity takes a different route. It quantizes spacetime directly, treating it as a network of discrete loops. This avoids singularities and explains how space emerges from quantum building blocks, but it struggles to incorporate matter and forces beyond gravity. Connecting it to particle physics remains challenging. Other approaches exist. Causal dynamical triangulations build spacetime from simple geometric pieces and evolve it through quantum rules. Asymptotic safety suggests gravity might remain well behaved at high energies through a special mathematical property. Emergent gravity frameworks propose that spacetime isn't fundamental, but emerges from more basic quantum information. Each approach possesses strengths and weaknesses. Each makes different forecasts about Planck-scale physics. And frustratingly, directly testing these forecasts is nearly impossible with current technology. The energies are too high, the scales are too minuscule. But cosmology supplies an indirect testing ground. The early universe naturally probed Planck-scale physics. If we can decode the messages written in the cosmic microwave background, in the spectrum of gravitational waves, in the distribution of large-scale structure, we might distinguish between competing quantum gravity frameworks. This is why comprehending what transpired before our bang matters scientifically. It's not just philosophical curiosity, it's a window into the most fundamental statutes of physics. The universe's genesis is the one natural laboratory where quantum gravity was fully operational, leaving fingerprints we can potentially read. The battle between quantum mechanics and general relativity will be resolved. When it is, we'll possess a complete portrait of how space-time and matter operate at all scales, and with it, we'll comprehend what nothingness really signifies in the deepest sense. One equation might hold the key. During 1967, John Wheeler and Bryce-DeWitt derived an equation attempting to describe the quantum condition of the entire universe. It's deceptively simple appearing, but it contains profound implications for cosmology and the question of genesis. The Wheeler-DeWitt equation treats the universe's geometry and matter content as quantum variables. Just as an electron possesses a wave function describing its possible positions, the universe possesses a wave function describing its possible configurations. The equation informs you how this wave function evolves, not in time, but in terms of relationships between different geometries. Here's the peculiar aspect. The equation doesn't contain time. There's no variable representing when things transpire. Instead, it describes correlations between different aspects of the universe's condition. It's sometimes termed the equation with no time, and it raises deep questions about whether time is fundamental or emergent. When applied to cosmology, the Wheeler-DeWitt equation allows solutions where a universe tunnels into existence from a condition with zero dimension. This isn't a metaphor, it's a quantum mechanical process analogous to how particles tunnel through barriers. The universe initiates in a configuration that classically couldn't expand, then quantum tunneling allows it to jump to a configuration that can. Alexander Vilenkin developed this universe from nothing scenario using the Wheeler-DeWitt equation. In his framework, the nothing is a quantum vacuum condition with no classical spacetime. The universe tunnels from this condition into a small closed space that immediately begins inflating. From our perspective inside the universe, it appears like time commences at the instant of tunneling, but calling it nothing is misleading. The quantum vacuum condition exists, it possesses properties, it's described by mathematical statutes. It's not absolute philosophical nothingness, it's the quantum mechanical ground condition before classical spacetime emerges. Other solutions to the Wheeler-DeWitt equation exist. The Hartle-Hawking no-boundary proposal uses imaginary time to smooth out the singularity. Bohm's pilot wave interpretation suggests the quantum potential in the equation acts like an effective cosmological constant. Each approach gives different insights into what the pre-classical condition might be. Chinese physicists Dongshan He, Dongfeng Gao, and Qing Yuxi published work during 2014 exploring spontaneous genesis solutions. They demonstrated that under certain circumstances, a Planck-sized vacuum bubble possesses a non-zero quantum probability of expanding rather than collapsing. Once expansion commences, inflation takes over and generates a universe. The probability is minuscule. But in a timeless quantum realm where all possibilities exist in superposition, minuscule probabilities become actual outcomes given enough trials. And in an eternal quantum foam of fluctuating vacuum conditions, every possibility eventually transpires. This supplies a mechanism for the universe's genesis that doesn't require an external cause. The quantum vacuum is inherently unstable. Virtual fluctuations constantly occur. Most collapse immediately, but occasionally by chance. One grows into an inflationary bubble that becomes a universe. The Wheeler-DeWitt equation is not a complete framework. It presumes a particular form of quantum mechanics and doesn't incorporate all aspects of quantum field theory, but it demonstrates that mathematics allows for spontaneous genesis of universes from quantum conditions. Whether nature actually uses this mechanism remains unknown. Testing these notions is extraordinarily difficult. The wave function of the universe isn't directly observable, we're inside it, part of it. We perceive its consequences, the structure of spacetime, the distribution of matter, but not the underlying quantum condition itself. Yet the implications are clear. The universe's genesis might be a quantum occurrence requiring no external trigger. The statutes of physics themselves might be sufficient to explain existence. Step back from the details and examine the landscape of frameworks: inflation before our bang, cyclic bounces, ekpyrotic collisions, eternal inflation multiverse, Wheeler-DeWitt quantum tunneling, loop quantum gravity bridges. Each framework is different, but they share a common theme. None of them require an absolute commencement. Our bang was a transformation, not a genesis. Before it came something else, whether inflationary vacuum, contracting universe, quantum foam, or colliding brains. And before that, possibly something else still. The chain of causation might extend infinitely into the past, with no first cause, no instant of genesis, no start to time. This challenges our intuition. We're accustomed to stories with beginnings, birth, genesis, first instance. But nature doesn't care about human narrative preferences. If the mathematics states time is eternal, then it's eternal. Alternatively, time might be cyclic or even illusory. Roger Penrose's conformal cyclic cosmology suggests the infinite future of one cosmic epoch becomes the bang of the next. Time loops back on itself. Julian Barber argues time is an emergent property of changing configurations, not a fundamental dimension. Different perspectives, but both suggest linear time with a definite start is naive. The philosophical implications are profound. If the universe possesses no commencement, then asking why it exists becomes peculiar. It exists because it always has existed in some form. Existence is the default condition, not something requiring explanation. Nothingness would require explanation. Why wouldn't quantum fluctuations, vacuum energy, or spacetime curvature exist? This reverses the usual framing. We've presumed nothingness is simpler than something, so existence needs justification. But in physics, empty quantum conditions are highly constrained. True nothingness, no fields, no vacuum energy, no quantum fluctuations, no mathematics, no statutes, might be impossible. It might violate consistency requirements we don't fully comprehend yet. If so, then something has always existed and always will exist. The universe transforms continuously. It traverses phases, expanding, contracting, bouncing, inflating, generating structure, dissipating into radiation, repeating. Each phase appears different, but the underlying reality persists. We find ourselves in an expanding phase seeded by a hot bang that was itself seeded by cold inflation. Trillions of years from now, dark energy might dominate completely, diluting matter to negligible density. The universe would become frigid and vacant again. Is that a conclusion, or just another phase transition preparing the circumstances for what comes next? If brains collide, another bang could occur. If quantum tunneling transpires, new inflationary bubbles could spawn. If loop quantum gravity is correct, maximum density could trigger a bounce. The universe would continue, just in different form. This portrait fits with deeper principles in physics. Energy is conserved, information might be conserved, fundamental constants seem constant. Reality possesses structure and follows rules. Why would that structure abruptly appear from nothing or disappear into nothing? The universe doesn't commence or conclude, it transforms. And that transformation is governed by principles we're gradually uncovering through observation, experiment, and mathematical reasoning. The question shifts from why is there something rather than nothing to what determines the form that something takes at any given instant. The answer to what existed before our bang is both simpler and stranger than absolute nothing. There was something, a quantum condition, a vacuum field, a contracting universe, a colliding brain, a timeless configuration space. The details remain uncertain. The framework differs between theories, but the conclusion is consistent. Nothing in the philosophical sense never existed and possibly cannot exist. The quantum vacuum won't allow it. The uncertainty principle prevents it. The mathematics forbids it. Reality at its deepest level is not vacant. It's not static. It's a dynamic system of fields and probabilities and geometry that never stops evolving. Our bang was one instant in this endless evolution, an important instant for us because it generated the circumstances for stars, worlds, and life. But not a special instant cosmically, just a transition, like water becoming steam, except what transitioned was space-time itself. Contemporary cosmology has pushed our comprehension back beyond the traditional bang to reveal a richer story. We recognize inflation transpired first, propelled by vacuum energy. We recognize the universe might be cyclic, bouncing or colliding through endless epochs. We recognize quantum gravity replaces the singularity with something finite. We recognize the vacuum contains energy shaping cosmic evolution. What we don't recognize yet is which framework is correct. Is it ekpyrotic collisions, loop quantum bounces, eternal inflation multiverse, Vilenkin tunneling? Perhaps multiple frameworks are correct in different regimes. Perhaps they're all approximations of a deeper framework we haven't discovered. Future observations will narrow the possibilities. Superior measurements of the cosmic microwave background, detection of primordial gravitational waves, more exact tests of dark energy, advances in quantum gravity frameworks, experiments pushing to higher energies. Each piece of data constrains which models are viable, but already we recognize enough to revolutionize how we think about Genesis. The universe didn't originate from nothing. It originated from something that transforms, that something has always existed. At minimum, as far as our physics can inform, the question isn't why existence rather than non-existence. The question is why this particular form of existence right now, and the answer involves quantum mechanics, gravity, vacuum energy, inflation, and possibly higher dimensions. It involves mathematics describing how fields evolve, how space-time curves, how probabilities collapse into actuality. It involves natural statute, not supernatural intervention, physical process, not metaphysical mystery. The cosmos is not a genesis. It's an eternal configuration of change, sometimes expanding, sometimes contracting, sometimes inflating, sometimes bouncing, always transforming, always existing, never truly commencing or concluding in any absolute sense. We're part of this transformation, temporary arrangements of atoms assembled by the cooling aftermath of one particular bang in one particular region of an infinite multiverse or one particular cycle of an eternal recurrence. We exist for a brief instant, aware and curious, attempting to comprehend the larger configuration we're embedded in, and what we've learned is humbling. We're temporary witnesses to an eternal cosmic dance. The universe is far older, far vaster, and far stranger than we imagined. Our bang wasn't the start of everything. It was barely even a start, just one more transition in a reality possessing no commencement and needing none. Nothing never existed. The void was never vacant. Reality is eternal transformation. And we're fortunate enough to witness one brief phase of it, That's what existed before our bang. That's what exists now. That's what will exist forever. Not nothing. Everything. If this journey through cosmic genesis has expanded your perspective, show your support by hitting that like button and join the Unfolded Late Science community for more mind-expanding explorations. The universe's deepest secrets are waiting.